Okay, so what we've done so far is we have looked at, so let me just put this so far, as with respect to legged machines. So first thing we looked at was passive walkers. Okay, which is basically the walkers which go downhill and they do not have any torques, and so they are they walk, but they're very fragile. You perturb them, they fall down. Then we looked at powered walkers. Okay, and so there were two powered walkers we looked at. One was the just a powered, I would call them machines. So we had a walker. So that walker was basically, you had a hip torque and a push off. Okay, and then I think there was a homework where you basically there's no torque. My bad. So there was no torque there. There was just p. So control variables were p and theta. Okay, so you could control the push off. You could control the foot step length, foot placement. And in the homework, you basically try to find a controller which gets you to track a reference by controlling this p and theta. Okay, and then we also did a hopper. So it was a spring mass hopper, and in which case you control the foot placement. So these things, p, theta, are controlled once per step. What I mean by that is you decide what foot placement you want, you set that foot placement, and then you get one step, and the next step you do the same thing. This is kind of very unconventional in terms of what we really see in other fields. For example, in mobile robots, we have to control the torque to the motors or voltage to the motors, which is a function of time. Or in case of a manipulator, you'll have to control the torque to the joint such that it moves from point A to point B. And so we've sort of ignored that aspect of control, which is when you look at machines like a walker, you actually don't have access to theta directly. The foot placement angle is a consequence of setting up a torque. So you set the torque, and then once you set the torque at the right value, you get a certain position. Now, if you had a servo motor, then you can just set the position. But a servo motor also requires some PID controls that it can actually take that position you ask for and then convert that to a torque, or a voltage or current, which it can use. But most of the times, our robots have some kind of a motor which has either a voltage or a torque or the current, and the current is actually, so modeling a motor is a separate issue, but let's just assume that we have a pure torque source. That is, our motors can provide torques. It cannot give us thetas and p's. So those have to be sort of computed by assigning the right torque. So our design problem is actually finding what torque profiles to put on the joint such that it will move the way we want to do. So this part is on low level control or joint level control. In other words, we are setting torque as a function of time. Okay. Now we have also seen torque as a function of time in the class where we talked about trajectory tracking. So you have a trajectory which could come from a polynomial or optimal control or trap well traj, and then you want to find a torque such that you can hit that trajectory. You can go along that trajectory, right? And so we did what is known as, so this can be thought of as trajectory tracking. Okay, well, by the way, this is just one way of controlling the system, trajectory tracking. There are other ways to do it without using trajectory tracking. We are only going to talk about trajectory tracking. And then we saw we have to track the trajectory. We could do a PID. We could do what is control partitioning. And really, control partitioning is favorable because we get this response where we don't have to think too much about controlling the torques. We can just put kp equals kd equals 2 square root kp, and then put the model, and then it will perfectly track. The problem with doing that for legged robots is that we have what is known as underactuation. Okay, so what is underactuation? Underactuation happens when the actuators are less than the number of joints. Okay, so for example, if you have a legged robot like this, okay, with 2 feet, it typically has one motor here, and that motor can apply a torque. But this point, which is the point foot, is not connected to the ground through a motor. So you cannot apply a torque. The motor torque at the joint is 0. So we have, in this case, 2 degrees of freedom. So theta 1 and say theta 2. But we only have one actuator. Okay. So if you want to do trajectory tracking now, there's a problem because you will not be able to control both the joints because you don't have 2 actuators. Now, this problem can be solved if you have like a foot and then you put an actuator here, then this can be controlled to some extent, but there's a problem with that, which is if you even have a foot and you have an actuator there, you cannot apply any arbitrary torques on that leg, because if you apply too much torque, what will happen is that foot will overturn. Okay, so when you're walking, you're not really applying any torque on your ankle, especially when you're you only apply that torque towards the end of the stance to push off, which is when your foot is already turning. But you don't do that when you're walking in the majority of the single stance phase, because that foot, so you can think of it this way. So if you have a leg and you have a foot, and then if you put a motor here, and then you start applying a torque, so this torque will generate the ground reaction force, and this is your length. Okay, so if you assume that your so in this case, my bad, the torque should be this way, because the torque will basically propel this forward, right? So it will generate a push off. So if the torque is this way, if the foot is massless, then you can see that for equilibrium, torque equals P times L, right? Because this foot is massless. So now what will happen is, as you keep increasing this, okay, the ground reaction force you have little control over. It's the L which will start increasing. The way L will increase is that this point will move to here. So this point is, by the way, known as the center of pressure. So the center of pressure keeps moving. At some point of time, it reaches the edge of the foot. And that's the edge of the foot. What happens is then your leg will rotate. To be here, and your foot will rotate. And so once your foot rotates, then you have underactuation here. Now there's no motor. So you can't really exploit that ankle. You can only do so much. You can only put so much torque. If you put beyond that, it's going to fail. So the best way of thinking of these robots now is to not think of the ankle for a second. Let's just look at this model. So it's the walker with a hip torque. So what you can think of this like this. There's a torque here, and there's nothing here. It's just a pin joint. Okay, so it has to move. Now, if you write we've derived the equations for single stance, we've derived the equations for foot strike. The only difference between a passive walker and this one will happen in the single stance phase. The equation will be something like this: m theta double dot plus c theta dot plus g theta. So it looks very similar like a manipulator. Okay, and then there is a torque. I'm just going to put a u in place of a torque. But the problem is that this torque, so this is typically two equations. So 2 by 1, and this will be 2 by 1. So it's going to be, and this actually is not 2 by 1, unfortunately. This is actually something like this, 0 and u. And 0 because this theta 1 is unactuated, and the second one is actuated by torque. So if you want, you can put torque there. Okay. So other way of people write this is actually they just write u for torque. This is u, or sorry, u is torque. And then they write what is known as a torque selection matrix. So if you put this as 0 and 1, you basically have 0 for the first row and then 1 for the u for the second row. So you write it as BU. Okay. So the typically the people, if you read papers, you'll see that people will write this equation as this. And I'm just going to combine this as n. Okay. They might have C and G. We're just going to club that all together. Okay. So they'll write it like this, but this is they call the selection matrix. It just helps you to keep track of which torques are actually affecting it. So this is the equation. Unfortunately, B is not 1, 1, which would be nice. And so we need to control the system. So the way we do this is, what we'll do is we'll use what is known as partial feedback linearization. What it means is that instead of, so you have theta 1 and theta 2 corresponding to the two links. So this is theta 1, this is theta 2. Okay. We cannot control theta 1 because there's no motor, but we can control theta 2. So what we'll do is we'll try to track theta 2 as best as we can. Okay, so this will be a joint level control. Okay, and then hope that theta 1, then hope that theta 1 is stable over the time scale of a step. Okay, so there are other ways of, so this is just a hope, but there are ways in which you can stabilize theta 1 also. You don't stabilize it you don't track it, but you stabilize it over one step or multiple step. And this was one of the homeworks you did. You basically control theta 1 to be whatever reference you wanted by just controlling the footstep and the push off. So that's a separate part. But for now, we're just trying to try to track theta 2 as best as we can. And I will show you that when you do that, you will actually end up making the system low dimensional. So even though the system has four numbers, right? Theta 1 dot, theta 2 dot, using the Poincare map, which is a surface at which you start taking the system, you start understanding the dynamics of the system about which you will see that the system dimension reduces to so this is 4, it will be 4 minus 1, and that's just because that Poincare map reduces dimension. So when you look at the eigenvalues, you see those eigenvalues are actually 3. That is, one eigenvalue will be 0. Okay. Now what I'll show you is that using PFL, we'll be able to reduce this eigenvalues from 3 to just 1. Which means that now we have reduced the dimensionality from 4 to just 1, and we only are worried about that one dimension to be stable. So that dimension is actually theta 1 dot. It's not theta 1. So what this partial feedback linearization will do is it will actually take an n-dimensional system in, say, a planar system, and then reduce it to just one dimension. So which is a nice thing. So let's see how this is done. Okay, so it's not much theory. So we have the equations. N equals pu. So we find theta double dot. So that's going to be pu minus n, and we take the inverse of m inverse both sides. So we get theta double dot. Now, what we do is we can divide this into two things. Theta equals theta 1 and theta 2. Okay, theta 1 is going to be our uncontrolled degree of freedom. Let me call it theta u. And the theta 2 is going to be my controlled degree of freedom, theta c. Okay, so what I'm going to do is I'm going to make theta c is basically theta 2, but theta 2 is some matrix times theta 1, theta 2. It's going to be 0 and 1. So let's call that matrix as SC, and this theta 1, theta 2 as my theta, because that has all the theta. So I can write theta C as SC theta. And so what I'm going to do is I'm just going to differentiate both sides twice. And since SC is a constant, it doesn't really, you don't have to differentiate that. So you get theta double dot. But theta double dot is equal to, from 1 is m inverse bu minus n. So from 1. Okay, so you got theta double dot. Now this is a trick, which is this is fully controllable. We can control theta c because we have a motor or actuator there. We just set that equal to whatever we want it to be, which is theta double dot c ref plus kp theta minus theta ref. So it's going to be all theta c's. Just write it above. I think this should be negative, and this should be negative kd theta c dot minus theta c dot ref. So this is the same thing we have seen before for feedback linearization, except that you only do one dimension, which is controllable to be this. So once you have theta double dot c equals this, now what you can do is you can actually, from this equation and this too, we can see that it's SCM inverse pu minus n equals theta double dot c ref. Instead of doing all this thing just to write the whole thing, I'm just going to call this whole thing as v. So this is equal to v. And my goal here is to solve for u. Okay, so what I can do is I can essentially multiply both sides. Sorry, expand the bracket and get, then move this second term to the left. And now to find u, all I need to do is I need to find the right inverse, which is basically take the inverse of this whole thing. And I'm hoping that this inverse is defined, okay? So you need to check that. It should be square. If not, you need to take what is known as pseudo inverse. Okay, so this is my control. This is the control that ensures theta c follows the theta c reference. Okay, and once you do this, you will see that the dimension of the system is over the Poincare map is actually not 4-dimensional or 3-dimensional, it's only 1 dimension. So I'm going to show you code. It won't take me much time. Let's see some code. This is a code which I took from the passive walker, and then I just put the controller. And the only change I think I made was the only change is that well, there might be a few more changes, but the main change I made was inside my single stance, I basically call controller, okay, which is the file I defined, just like I called the other file manipulator. And this controller function basically does that equation. Now, I did use a 5th order polynomial to get the trajectory. So instead of using other techniques, I used the 5th order. So which basically gives me this theta double dot to ref and so on. And then I got the, let's see. So I got the mass matrix, I got the n, which I showed you. I got the KPKD, B and SC is defined as I wrote down on there, and this is basically my control, which is exactly the same formula I derived. Okay, so it's going to take that as output from single stance, then that U will actually go into my equations, which are defined here. So these equations, as I said, came from passive Walker. Okay, so here I've done quite a few things. First, I do is I showed you the passive gate. Okay, this is as I said, copied from the earlier files. So if you run this, it will give you the solution we got for the passive gate. So it'll give me the Jacobian, it'll give me the eigenvalues, and then what I do is I then set up this controller, which is partial feedback linearization. I find the new fixed points because now the fixed point would change as I have a controller in place. Then I show you the Jacobian of that and the eigenvalues. So if you compare this eigenvalue with the previous one, you'll see that the eigenvalue is actually has only one dimension. And then I do some forward simulation. So let me run this. Okay, so actually what I did was I actually perturbed the system. So I started off with a start which is not on the limit cycle, and then I showed you that by putting this controller, you're able to get back to the nominal gate. Now, if there was no controller in this system, it was passive, then it would actually fall down. So the controller is helping, and so this is a fixed point for the uncontrolled systems, the passive system. It has four eigenvalues, but one of them is zero. So in fact, there are three eigenvalues: 0.65, 0.65, 0.41. 0.65 is the highest eigenvalue, which basically is to be used to understand the stability. Since it's less than one, the system is stable. Now, then I found a new fixed point. Okay, this fixed point had these eigenvalues, and I can see that three eigenvalues are actually zero, 1e, negative 10, and so on. So only one eigenvalue is non-zero, and that eigenvalue is 0.25, which is smaller than the eigenvalue I got here, which is 0.65. So this is much more stable than the previous controller. And then what I do is I actually perturb the system and then get it to simulate, and then it's basically showing how the system is uh, is controlling itself to not fall down. But then the best figure which actually illustrates this is, I think, is figure 3. This picture shows how theta, if you start here, then how theta one dot changes in theta 1 dot plus theta 2, which is basically the absolute angle of the swing leg, changes as a function of state. So this is known as a space. It's called I forget the name, but this is basically not a time-based plot, but it is a state-based plot. Theta 1 dot versus theta 1, and theta 1 plus theta 2 dot versus theta 1 plus theta 2. I think it's called phase plot.